Hello everyone, welcome to this video lecture on analysis of convective heat transfer, where we will be discussing on how to solve numerical problems in convection mode of heat transfer easily. I am Dr. N. Gunasekar, working as Associate Professor in the Department of Mechanical Engineering, Sri Ramakrishna Engineering College, Coimbatore. We all know thermodynamics discuss on how much heat is transferred and how much work is done and what is the final state of the system. So thermodynamics does not say anything about how the heat transfer happens or how much time it will be taken for heat transfer to happen, or otherwise it doesn't say about what are the modes in which heat transfer happens. So all these things will be taken care in the heat transfer. So heat transfer says about how the heat is transferred, what is the mode of heat transfer, then it also says about what is the time taken for the heat transfer to happen. See, the application of this heat transfer will be used in designing of thermal equipments or otherwise HVAC systems like that. So first let us see when does this heat transfer happens. So we all know that the driving potential for fluid flow is nothing but the pressure difference. Similarly, for current to flow there should be voltage difference. So heat transfer will happen as long as there is a temperature difference. The important point what we have to keep in mind is heat transfer happens as long as there is a temperature difference, and it also happens always from higher temperature to lower temperature according to the second law of thermodynamics. The three modes of heat transfer are conduction, convection and radiation. So you see, conduction heat transfer to happen we need matter. So basically you have to understand conduction mode of heat transfer happens without a molecular phenomenon. That means if you take a solid, if we hit one end of the solid, after some time we can feel the heat at the other end. So the heat transfer happens from one end to the other end due to the molecular interaction. So this conduction mode of heat transfer mainly happens in solids. So but that doesn't mean that there is no heat transfer by conduction in liquids or gases. There will be conduction mode of heat transfer in liquids and gases, but the value will be very less. The reason being, in solids we know the molecules are very closely packed to each other. On the other hand, if you take for liquids or otherwise for gases, the molecules are loosely packed. So therefore the amount of heat transfer by conduction will be very less. The next mode of heat transfer is convection. So the convection heat transfer involves the bulk motion of fluid. If you compare this conduction is a microscopic approach where we cannot visualize the heat transfer happening. On the other hand, if you take convection, we can visualize the heat transfer. Suppose if you take an example of you are heating the water in a pan. We can initially observe for some time there will not be no water motion, but after some time you can see the water moving from bottom to the top, from the top to the bottom. The reason for this motion is due to the density difference. The driving force here is density difference. The density difference means we all know that when a fluid is heated, its density will tend to decrease. So therefore that fluid will tend to move upwards. On the other hand, fluid which is on the top will have high density, that will tend to move downwards. By the way, the bulk motion of fluid will happen. So please keep it in mind, convection involves fluid matter. It mainly happens between a solid and a fluid and within a fluid. The next mode of heat transfer is radiation. So the radiation mode of heat transfer compared to the conduction or convection does not require any matter. So it happens in the form of electromagnetic waves. The example for radiation is the heat we receive from the sun. We all know that sun is at a very high temperature, whereas our human body will be at a low temperature. We can receive the heat. In between there is no medium, but still we are receiving the heat from the sun. So therefore the heat we receive from the sun is a classic example of radiation. Now we can see the governing laws of the three modes of heat transfer. The conduction mode of heat transfer is governed by Fourier's law, which is given by Q is equal to minus K into A minus Ka dt by dx, where this K is nothing but K stands for thermal conductivity. K stands for thermal conductivity. This A stands for the area perpendicular to the heat transfer, and this gt by dx is nothing but this is the temperature gradient. This thermal conductivity, which unit is watt per meter Kelvin. We can see this thermal conductivity and Q are directly proportional. Similarly, this area perpendicular to the heat transfer is also directly proportional to Q. So a material which is having a higher value of K, that's higher value thermal conductivity, will transfer more amount of heat. So we can see thermal conductivity is a property of a material. Different materials will have a different value of thermal conductivity. For example, there are certain cases where I want to reduce the heat transfer. I want a material to reduce the heat transfer. There I will use a material which is having a low value of thermal conductivity. On the other hand, there are certain applications where I want to increase the heat transfer. There I will use a material of having higher thermal conductivity. The thing what is to be kept in mind is this K is a property of a material. Different materials will have a different value of thermal conductivity. These data are just like the density or just like viscosity. This thermal conductivity is also a property of a material. The next convection mode of heat transfer is governed by this Newton's law of cooling, which is given by Q is equal to H into A into delta T. This H is nothing but convective heat transfer coefficient. Convective heat transfer coefficient. As just like that here, what we are discussing in Fourier's law, here also we can observe this H and Q are directly proportional. Higher the value of H, higher the value of Q. Now this A I will put as AS, which is nothing but surface area exposed to heat transfer. Higher the surface area, higher the heat transfer. Delta T is nothing but the difference between the hot surface and the fluid. So this is the Newton's law of cooling. We are going to detailedly discuss about this convection, that's a Newton's law of cooling. What are the steps involved in analyzing? So what are the parameters which decides this H? That is what we are going to discuss in this lecture in detail, that we can see afterwards. Next, the radiation mode of heat transfer is governed by Stefan-Boltzmann law, which is given by EB is not equal to sigma into Ts power 4, where EB stands for emissive power. This sigma is nothing but Stefan-Boltzmann constant. Stefan-Boltzmann constant, and this Ts is the absolute temperature in terms of Kelvin. So we have seen the governing laws. I can say again, I can reiterate, the thermal conductivity decides the conduction heat transfer. Similarly, the convective heat transfer is decided by this heat transfer coefficient H. As we discussed earlier, the convection heat transfer involves the movement of fluid. So as long as the fluid motion happens, the convective heat transfer happens. So it is a mechanism which involves the presence of a bulk motion of fluid. We all know that what is meant by land breeze and sea breeze. During daytime, the land near the near the ocean will get heated up fastly. So therefore, what happened? The air start to move from the land to the sea. The reverse happened during the sea breeze. That is a classic example of the convection mode of heat transfer. See, there are two types of convection. First one is the free or otherwise natural convection. The second one is the forced convection. So how this classification is made means, see, we all know that convection involves the mixing of fluid. Convection involves mixing of fluid. How this mixing of fluid, whether it happened due to the external force what we apply or it happened due to the buoyancy effect, based on this only the classification is made. If it is the fluid motion happens due to this buoyancy force, then it is called as the free or otherwise natural convection. On the other hand, if you use an external force, say we are using a fan to blow air, or otherwise you are using a pump to pump the fluid inside some tubes, that is a case of a forced convection. So basically how this fluid motion happens, that is what which decides whether it is a free convection or otherwise it is a forced convection. As we have seen, again I will reiterate what is this Newton's law of cooling. Q is equal to H into A into delta T, where H is the convective heat transfer coefficient whose unit is watt per meter square Kelvin. The A is nothing but the area exposed to heat transfer whose unit is in terms of meter square, and delta T is the temperature difference between the surface and the fluid. So you can see H and Q are directly proportional. Higher the value of H, higher the value of Q. Area is directly proportional to Q. Higher the area, higher the value of Q. Delta T is the higher the value of delta T, higher the value of Q. Normally the convection mode of heat transfer is very important while we are designing a cooling system for electronic component, or otherwise as we are seeing now, the battery management is playing a major role in electric vehicle design. So therefore the mode of heat transfer is convection. So we should know what are the parameters which decides this convection. That is the idea of presenting this lecture. Now you can see this H, convective heat transfer, it is not a property like thermal conductivity. As I said earlier, the thermal conductivity K in conduction is a property. If you take an aluminium, it will have some value of something around 280 to 300 watt per meter Kelvin. If it's a copper, its value will be something around 300, like that. On the other hand, H is not a property. That is the thing what I am trying to say here again. H is not a property. It is not a property. It is not a property like thermal conductivity. It depends upon several parameters like what are the fluid properties. Say what are the fluid properties. Let it be a viscosity, thermal conductivity, density, or the specific heat. We all know that air will have a different value of viscosity compared to that of water. Similar thing can be said about thermal conductivity of water and air. So therefore, the fluid property has a role in this convective heat transfer coefficient. The next is the flow parameters. How the flow happens, or whether the flow happens as a laminar or turbulent. We will discuss on this laminar and turbulent afterwards, but as of now you can see the flow parameters will also have a major role in this convective heat transfer coefficient. Next is the surface characteristics. What are the surface characteristics? Whether the surface is rough or whether the surface is smooth. What is the orientation of the surface? So it's the same. The surface which is surface which is circular will have a different value of convective heat transfer coefficient compared to if it is in a flat surface. So all these parameters will have a major role in deciding this H, which will have a major role in the value of heat transfer. Now this slide shows some typical values of convective heat transfer coefficient. So you can see it's an interesting slide where you can see for a free convection the convective heat transfer coefficient for gases it will be 2 to 25, whereas for liquids you can see it will be from 50 to 100 watt per meter square Kelvin. On the other hand, if you see for forced convection the values will be from 25 to 250 for forced convection for gases. On the other hand, for liquids it will be from 50 to 20,000. Just we can compare, you can see for the gases the free convective coefficient value will be from 2 to 25, whereas for gases in case of forced convection the value is 25 to 250. The reason being, in free convection the driving force is only the density difference. The driving force for free convection is driven by the density difference. On the other hand, if we take a case of a forced convection, we are using some external aid. Say we are using a fan, or otherwise you are using a pump to ensure the mixing of the fluid. So therefore, the convective heat transfer coefficient of forced convection value will be very higher than that of the free convection value. So if we take a boiling and condensation, see boiling and condensation are another important phenomena where there will be only change in phase. There is no change in temperature. Boiling is nothing but change in phase happening from liquid to vapor. On the other hand, condensation is the phenomenon which happens from change in phase from vapor to liquid. In both the cases there is no change in temperature, only the change in phase. The convective heat transfer coefficient value we can observe, it's a very very high value, something around 2500 to 1 lakh watt per meter square Kelvin. The data whatever that we given here are only the ranges. Just keep it in mind, I have not given the exact values of convective heat transfer coefficient for gas. If it is free convection, we have given just the range. For gases, if it is free convection, maybe from 2 to 25. If it is a liquid mean, the value will be from 50 to 100. If it is a forced convection value, for the gases, the value will be from 25 to 250. On the other hand, for liquid, it will be from 50 to 20,000. So these are the range of the convective heat transfer coefficient, not the exact value. Again, I am saying just we can compare the value of K and H. K is a property. For aluminium, this is the value of K. For copper, this is the value of K. This all will come in conduction mode of heat transfer. But I cannot say that for water this is the value of H, for air this is the value of H. I cannot say. It depends upon the other parameters also. The convection mode of heat transfer depends upon several dimensional numbers. We are going to see what is the significance of each and every dimensional numbers. For free convection, the Nusselt number is a function which depends upon this Grashof number and Prandtl number, whereas for forced convection, Nusselt number is a function which depends upon the Reynolds number and Prandtl number. Now let us see what is meant by Reynolds number, what is the significance of Reynolds number, what is meant by Grashof number, what is meant by Prandtl number. All these things we will see one by one. First, let us see what is my Reynolds number. So we all know that convection mode of heat transfer depends upon the mixing of the fluid. Higher the mixing, higher the heat transfer. Now we have to keep it in mind the flow. There are two cases of flow. The flow may be either laminar or flow may be turbulent. In laminar flow, the flow will happen as a lamina of sheets, where in laminar flow the value of mixing will be less. Less mixing will happen. On the other hand, if we take turbulent, the mixing will be more. There will be more amount of mixing. So as long as the mixing of fluid is more, the heat transfer rate also will be more. So this Reynolds number only will decides whether the flow is laminar or turbulent. The next number what you are going to discuss is Nusselt number, Nu, which is nothing but the ratio of conductive heat transfer to conductive heat transfer. So the Nusselt number value, its significance is it describes the enhancement of heat transfer because of convection in comparison to conduction. That means when Nusselt number is equal to 1, when Nu is equal to 1, the heat transfer by conduction is equal to heat transfer by convection. When Nu is greater than 1, the effect of heat transfer by convection is greater than that of the conduction. So higher the Nusselt number, higher the heat transfer will be. The next number what we are going to discuss about Prandtl number, PR. So what is the Prandtl number? It is the ratio of momentum diffusivity, the ratio of momentum diffusivity to thermal diffusivity. So it describes the thermal boundary layer. See, boundary layer is nothing but a layer which develop on the surface due to either. There are two type of boundary layers. One is the velocity boundary layer, that is which happen due to the difference in velocity. Other one is we can call this velocity boundary layer also as a hydrodynamic boundary layer. Hydrodynamic or otherwise velocity boundary layer. The next boundary layer is thermal boundary layer. Thermal boundary layer. So what is meant by this velocity hydrodynamic boundary layer means the boundary layer which has formed due to the difference in velocity is called as a hydrodynamic boundary layer. On the other hand, the boundary layer which has developed due to the temperature difference between the surface and the fluid, that is called as a thermal boundary layer. So this Prandtl number only will relate this hydrodynamic boundary layer and thermal boundary layer. When I say PR is equal, Prandtl number is equal to 1, it means the hydrodynamic boundary layer, that I will put it as notation delta. The thermal boundary layer I put delta is delta TH. Now you have to understand, when PR is equal to 1, then your hydrodynamic boundary layer will be equal to thermal boundary layer. So when Prandtl number is equal to 1, your del is equal to del TH, that is hydrodynamic boundary layer will be equal to thermal boundary layer thickness. So significance of Prandtl number is to understand the relationship between hydrodynamic and thermal boundary layer. The next number what we are going to discuss is about a Grashof number. This Grashof number will have the same role as that of a Reynolds number in case of a forced convection. It is a ratio of buoyancy force to viscous force. This ratio of buoyancy force to viscous force. This Grashof number is used to analyze the flow in terms of natural, whether the flow is laminar or turbulent. For identifying that, in natural convection we are using the Grashof number. Next number which you are using in free convection is the Rayleigh number, which is nothing but the Rayleigh number is the product of Grashof number and Prandtl number. Means I can say RA is nothing but is equal to Grashof number into Prandtl number. So this is again used to identify whether the flow is laminar or turbulent in case of a free convection. So if you see, again I will reiterate the point, for a free convection, Nusselt number is a function of Grashof number and Prandtl number, whereas for forced convection, the Nusselt number is a function of Reynolds number and Prandtl number. So this Grashof number is replaced by Reynolds number in case of a forced convection. Prandtl number remains the same. That is the important thing which you have to understand. Grashof number plays a major role in free convection. Similarly, this Reynolds number plays a major role in forced convection. So now I have taken an example of how to solve a numerical problem in convective heat transfer. Here they are given, the problem I have taken is the air at a temperature of 20 degrees Celsius is flowing over a flat plate which is 200 mm wide and 500 mm long. You can see the length of the plate is 500 mm and the width of the plate is 200 mm. The air which is given by, which is the fluid flowing, is a temperature of 20 degrees Celsius. The velocity with which it is flowing is at 2 meters per second. For this condition, we have been asked to find what is the heat transfer from the plate. That is the first case. Now, the second case, what they are given is the plate, the orientation of the plate is changed in such a way that the air flows over the 200 mm length side, and what will be the change in the heat transfer that is going to happen. That is what we are going to analyze. So here what we are going to see, you are going to see what are the procedure involved in this solving this heat transfer. Now let us see what are the steps involved in solving the problem which I have given earlier. The first point what you have to understand is we have to identify the type of convection, whether it is a free convection or forced convection. If the velocity value is given, the point which you have to make it is, if the velocity value is given, that is the case of a forced convection. On the other hand, if they said that nothing is said about the velocity, if it is given that a person stands in a still air like that, means that is the case of a free convection. For a forced convection, Nusselt number is a function of Reynolds number and Prandtl number, whereas for free convection, Nusselt number is a function of Grashof number and Prandtl number. If at all, if you take the correlations wrongly, instead of taking the correlation for free convection, if you use the correlation for forced convection, instead of calculating this Reynolds number, if you calculate the Grashof number, the entire problem goes wrong. So therefore, the first and foremost point which you have to keep it in mind is identifying what is the type of convection. The second point what we have to discuss is we have to understand what is the type of flow, whether the flow is external flow or internal flow. Some classic ways of how to express external flow is the flow happening over a plate, the flow happening over a cylinder, the flow happening over a sphere. Such cases are nothing but external flow. Internal flow means the flow happening inside a tube, inside a pipe, inside a duct. These are all the case of internal flow. Correlation, just like what you have seen for free convection, forced convection, the correlations for external flow and internal flow are also different. So identify what is the type of flow. Now for the example what we have taken, here, the flow is happening over a flat plate, So therefore it is the case of external flow. The case of external flow. Next, the velocity value is given as 2 meters per second. So therefore it is the case of a forced convection. These two we are observed first. Let us see what the next step is. The third step is calculating the property of the fluid. What is the mean temperature or what is the film temperature of the fluid? TF stands for the film temperature. We have to see what is the film temperature. The point how to identify, calculate the film temperature is nothing but TS is nothing but surface temperature. On the other hand, T infinity is nothing but fluid temperature. So we have to calculate the film temperature, which is nothing but the average of the surface temperature and fluid temperature. So the properties which you have to take are density, kinematic viscosity, thermal conductivity, Prandtl number and specific capacity. All these data can be taken from the standard HMT data book. We have to see what is the fluid, whether the fluid is air, whether the fluid is water or whether the fluid is oil. We have to check what is the fluid, and for that particular fluid we have to take all these properties. Instead of taking the fluid property for air, if we take as water, means the problem will get wrong. So therefore, we have to be very careful in understanding what is the fluid and taking the property corresponding to that fluid from the table. The next step is identifying where the flow is laminar or turbulent. As we have seen earlier, convection mode of heat transfer is governed by mixing of fluid. It depends upon how the mixing happens. In laminar, the mixing will be less. On the other hand, the turbulent mixing will be more. So therefore, the Reynolds number will play a major role in identifying where the flow is laminar or turbulent in case of a forced convection. On the other hand, so first let us see what forced convection, what are the correlation. If the flow happens in a flat, over a flat plate, then the Reynolds number value, if it is less than 5 into 10 power 5, please understand, if the Reynolds number value is less than 5 into 10 power 5, the flow will be laminar. If the Reynolds number is greater than 5 into 10 power 5, the flow will be turbulent. Both these Reynolds number values are only when the flow is external flow. That too over a flat plate. The critical Reynolds number will change for different configuration, different geometry. What I have given here is a sample of taken the problem of a flat plate. So therefore, the steps here given are currently corresponding to the flat plate. Next, if you go for internal flow, the flow happening inside a tube, or otherwise happening inside a pipe, inside tube or pipe, that is the case of an internal flow. For that such type of flow, the flow will be laminar if the Reynolds number value is less than 2000. On the other hand, the flow will be turbulent if Reynolds number is greater than 2300. So the point what we have to understand here is we have to identify where the flow is external flow or internal flow. So based on that only we can choose a correlation for this. The next we can see what is the value of identify whether flow is laminar or turbulent. For free convection, the Rayleigh number, RA is nothing but Rayleigh number will decide whether the flow is laminar or turbulent. So the flow happens over a vertical plate or vertical cylinder, the Rayleigh number lies between 10 power 4 and 10 power 8, the flow will be laminar. On the other hand, if the Rayleigh number lies between 10 power 8 and 10 power 12, the flow will be turbulent. Both this Rayleigh number value for flow to identify whether this laminar or turbulent, it is only for a flow happening over a vertical plate or vertical cylinder. If the configuration is something different, means the Rayleigh number value also will change, whether the flow is laminar or turbulent also will change. The next step is calculating what is the Nusselt number. Nusselt number is nothing but it's for free convection, as we have discussed. Nusselt number depends upon this Grashof number and Prandtl number. For forced convection, Nusselt number depends upon Reynolds number and Prandtl number. So we have to choose an appropriate correlation from the data book based on the calculated what is the Reynolds number to identify the flow is laminar or turbulent, based on whether internal flow or external flow. We have to choose an appropriate correlation from the data book which suits us the best. The next step is using this Nusselt number to calculate the convective heat transfer coefficient. If the flow is assumed, for the given case, if it's a case of an external flow, for external flow, Nusselt number is equal to H into L by K, where this is for external flow. What I have given here is for external flow. If the flow is internal, if it is for internal flow, Nusselt number is given by H D by K, where H stands for convective heat transfer coefficient, L stands for length of the plate, and K stands for the thermal conductivity of the fluid which is flowing. If it is an internal flow, this Nusselt number is equal to H D by K, where D stands for the diameter of the tube. It's an internal flow, it may be diameter of the tube or diameter of the pipe, or otherwise hydraulic diameter in case the flow happens in a non-circular section. So based on the correlation which we have used earlier, we have to calculate the Nusselt number. From the Nusselt number, you have to calculate the H. This is the unknown here, convective heat transfer coefficient H. Once the value of H is found out, means then we can use this Newton's law of cooling to identify what is the value of Q is Q. Q is nothing but H into A into delta T. So therefore, we have to understand the problem, read the problem clearly, understand, and then we have to proceed. Once this procedure means, if follow this 7 procedure means, then we can easily find out what is the value of Q, which can be used to analyze the convective heat transfer. I thank you all for spending your time to look at this video, which helps you in making you understand the analysis of convective heat transfer. Convection plays a major role in designing of a battery cooling system in case of electric vehicles or there is electronic cooling systems. So therefore, if I have just explained what are the steps involved in analyzing the convective heat transfer. Thank you.